Hey everyone, I'm David Room. Today we're gonna be doing some more um, 3D mesh processing stuff in Python, and I have kind of an interesting project or goal here in building some functionality in my personal uh, representation that I use for meshes and scene graphs. And I thought that this stream might be a good opportunity to talk about the functionality that's there, why I built it myself versus using some kind of known format, and then get into it a little bit by extending it and adding some new functionality. I hope everybody's having a good Thursday. I'm having a really nice week this week, and I've had some time to get into some aspects of my project that I haven't gotten a chance to work on for a while, and I'm having fun with that. So it's been a good week. All right, so let's hop right into it here. So for anybody who might be new, I have this ongoing project. It's a sci-fi world multimedia project that I've written a couple of books in. I'm making a sort of retro style space combat RPG, and I also do kind of higher detail 3D art for. And the unifying factor to a lot of this is I'm a software engineer by trade, so I like programming, so I like doing a lot of things with code. And the big thing that kind of got me into this 3D art and game development stuff is that I realized that I could actually do a lot of these things with code rather than doing them, manually. Like instead of clicking and dragging my mouse around in Blender for an hour, I could write a bunch of code that could be reusable and um, extensible, and I could remix things and remaster things. And when I build different functionality, it could kind of be reusable, and each piece that I build could kind of build on all of the other pieces. So I'll just show you a little bit of what this looks like. So just as an example, so I've been working on a big capital ship for the game, and it is called the Ashinoko, and whoops, um, and the way this ship is created is with Python code. So there's this module called ashinoko.py, and it's about 700 lines of Python code, and of course it's using other libraries and things that I've built and things that are in other existing libraries. I have a workbench script that when I run it, it's going to construct parts and data by calling the Ashinoko function, and then I can call this function called view parts to view it. And I'm actually going to just double check something quick because I was experimenting here with some alpha transparency stuff with these colors. But yeah, so let's take a look. If we run this script, let me zoom in here a little bit in the console. So if I run my bench script, this function gets called, and I get this 3D model in the viewer. That's pretty cool, right? So how is this actually represented? And I can actually even view this in Blender, and you can see that this is a hierarchy of multiple parts. It's not a single mesh. There's a lot of different components, and we can see it in the game with the ship viewer. So I can select the Ashinoko class and there it is. So how does this work? Well, to represent a collection of 3D objects, we need some kind of data structure that can do that. And I wanted to be able to write code to build these data structures and build them in a way that is the way that I want to work with data. So I made my own format, and I call that format parts. I like simple names for things, so it's parts. Let's take a look at how parts works. So parts is very simple, and this is all the stuff that's distinct to parts. It is a Python module that's also about 1,100 lines long, but there's certain parts of this that are kind of like more important than others. At the core of it is these two classes, and I'm not a huge fan of object-oriented programming in general, but I like using classes and objects for what I call records, where it's basically just a collection of fields. You may or may not modify them once they're created, but it's just basically a simple set of data. And then rather than having methods in those classes, I just have functions that operate on them. So our main component here is called part, and I'm using adders for this. Adders is a library that adds data class type functionality to Python. Now, I've been using adders for many years. Since I've been using adders, data class functionality was added to Python. So you could just use data classes for this. I've stuck with adders because I like it. I like the syntax of it a little bit better than data classes, and I'm familiar with what it does, and I don't really have a reason to change it. So there's that. But if you're familiar or if you've heard of Python data classes, it's the same kind of thing. So our main thing is a part, and the part can have a model, which can be a number of different things. It can be either a mesh or a string, a list, a dictionary. Those are sort of other types other than 3D meshes of things. It has a parent, which is basically the name of the model that is its parent, or the part that is its parent. A transformation, which is also optional. You know, if it's not present, it's just the identity transformation, and transformations are defined here as a rotation and translation. I'd like to get rid of some of this optional stuff here eventually. There's some redundant behavior in that the transformation itself can be optional, and the rotation and translation of the transformation can be optional. And you could actually have these things also filled in with identity values, and it would do the same thing. So I don't like that redundancy. It'd be good to get rid of it, but it is what it is for now. And then we also have props, which is just a dictionary of string keys that map to any kind of values, so you can store additional information. And then when we're talking about a collection of parts or a scene graph, it's just a very simple data structure that's just a dictionary of string keys. That's the name of each part to the part itself. And for a long time, the way I used this was each part sticked was just basically a single hierarchy. So you could kind of assume that within a single part sticked, there was just a tree of like a single tree, like with a single root of models. A recent change that I made, I updated it so that a part sticked can hold multiple, have multiple roots, and I built some functions for dealing with that. And that's just kind of a convenience thing, where just 1 second. I'll be back in just a second. Hey, could we not do that? Okay, my little son has a ukulele, and he's playing that right now. It's hard for me to think with musical instruments going on in the background. So, um, yeah. So we can have multiple trees with multiple roots in a single parts dictionary, and that's not really necessary, but it's kind of a convenient way to handle things. Um, Sometimes you want to have more than one thing in one of these sets, and it's just more convenient to be able to do that. But you don't have to. If you wanted to have a convention where you said, I'm only going to have one root in a parts dictionary, you could, and you could easily verify that. And these are some of the different model types that we can have. So like if the model is none, it's an empty. That's basically just like, you know, like an empty in Blender. It's just you can think of it as just like an empty node that, you know, doesn't have a 3D model itself, but could have multiples. Mesh is of course like a 3D mesh. Instance is like you can basically reference other meshes by name. And then we have like bones and graphs, which are kind of correspond to things in Blender, because this is sort of an intermediary format that I can use to describe things for Blender. And then also mesh list, which I don't know if I really use anymore. You can have a model be a list of meshes rather than one. This is something that is kind of on its way out. I think there's one or two places where I use it that could be easy to get rid of. And basically we just have a kind of a basic set of functions. I mean, the main thing that we want to do with this is be able to, you know, export it to different formats. So if we want to be able to export it to Blender or to the game engine, then we want the ability to you know, find the global transformation of each part in the hierarchy. So we have this kind of recursive functionality where we build up a cache of the transformations of the individual parts and can find kind of fill in that dictionary using that cache. And we also have functionality for combining transformations together. To be able to do that, this is kind of important because there are a number of different formats that those transformations can take. So if the rotation in the transformation can either be a matrix or a quaternion or Euler angles, so it kind of handles the conversions to rotation matrices to do that. And then it also is handling just the idea that you know, there's a little bit of a gotcha here. So like when we're describing a part, it is like rotated first and then translated to where it goes. So the rotations happen in the frame of reference of the parent. So there's a little bit of logic that has to be that is sort of required. So like if let's see here, R0, yeah, so like, and then we have to transform the positions as well. So yeah, there's a little bit of a gotcha sometimes. I think it's also, we're also able to handle, we're not necessarily assuming that positions are numpy arrays that we can just add together, so we're handling that. This could probably benefit with a little bit more like assertions about what the types of things are, and then some of this could be handled a little bit more clearly. And then And then we have a number of functions for just viewing. So there's a viewer in some of the other modeling utilities that I've built that is a wrapper around the PyRender viewer, where it basically just assigns it a basic material, basic gray color, and then views a mesh. So a lot of our functionality here deals with taking that part set and then flattening it down into a single mesh, right? So we have like this hierarchy of meshes, but we want to transform them all into the global coordinate system, concatenate them together, and then view it as a single mesh. This is viewing parts individually, which I don't know if I even use anywhere anymore. So this could probably go. And yeah, so here's flattening. So there's a function called flatten parts trans that basically finds all of the like individual roots and then flattens each tree of meshes into a single mesh. And find offset is kind of a slick thing. So this is kind of for handling that that multiple roots functionality. So when we do this view, it will automatically kind of line up the multiple roots so they're easy to view. Need to fix this. So find let's see. This is just, you know, grouping parts by the root that they belong to. Some functionality for prepending a part or set of parts to a parts dictionary, viewing a part set while adding a parent. So this happens sometimes, like if you're building a set of parts that you know you're going to concatenate into another set that have a certain parent, then you might want to view it and just add that parent in while you're viewing it. Kind of pretty printing type functions, summary of the different types of parts. This is kind of useful. So like if we have if we are reusing if we're reusing the same mesh within a set of parts, we can collapse those like repeated uses of that into instances so that when we save it out, we're not redundantly saving the same mesh. That's what this function does. And this is kind of a helper for that, so it traces a mesh back, you know, a model back to its original mesh. Scaling parts, scaling both the mesh and the transformation is something that happens. So like if you have a whole hierarchy of parts and you want to scale it, you have to scale the translations as well. And then yeah, here's flattening, so you can, you know, find a global transformation for each part, then get the mesh, transform it by that global transformation, and build a set of results that can then be flattened down. Just various functions for applying transformations, and these are just mainly dealing, you know, the only complexity here is just dealing with the fact that there might be different types of transformations. And actually, I'm gonna get a drink real quick, and then I'll be back and I'll dive into this and explore how it works. Okay, so how do we actually transform a 3D model? So the sort of most easy to apply way of transforming a set of points is using a rotation matrix. And actually, this is the inverse one. Let's look at the forward one. Yeah, so we rotate first, apply the rotation first, and then apply the translation. So whatever form the rotation is in, we're going to convert it to a rotation matrix. Yeah, and this converts either Euler angles or quaternions to a rotation matrix using functionality that's in trimesh. Quaternion is a really nice representation of 3D rotation. It's used a lot for cameras and for when you're interpolating between rotations. That is basically 4 floating point numbers. Euler angles is 3 floating point numbers, and I use the convention of Panda 3D, which is the game engine that I'm working with, where it is basically, they call it HPR, so it's like a heading, pitch, roll, intrinsic Euler angles. And you can convert either of those representations to a 3x3 matrix of numbers. That's a rotation matrix. And then what does it look like to actually apply that to a mesh? Well, okay, so another question is, what is a mesh? So how do we represent a 3D model? Well, I have a very simple representation of a mesh, which is, it is just a tuple of vertices and faces. And what are vertices and faces? Well, they're just numpy arrays. So vertices is a n×3 array of floating point numbers. So if you have n vertices, you have a 3D coordinate for each of them. That's your n×3. Faces is also an n×3 array, or m×3, I guess, because you don't necessarily have you don't have the same number of faces as vertices, but instead of floating point numbers, they're indices. So basically, just each row of that array are indices into the list, or the array of vertices, and each row represents a triangle. Now, there are a lot more efficient and complex ways to represent meshes, but we're not doing real-time work here. We're sort of doing this programmatic mesh creation, and this is a simple way to do things that makes meshes really easy to work with. It's very easy to interact with numpy arrays in different ways. You can filter them and plot them and do different things like that. So it's a good simple representation. And so how do we actually transform the mesh? Well, so translating is really easy. Basically, your mesh is a tuple of vertices and faces. You just pull out the vertices and you add the translation in, and then you put the two back together. Rotating is a little bit more complicated. So again, I'm going to assert that the rotation matrix is 3x3, pull out the vertices, rotate them, and then put them back together. And here we follow this convention. So we're going to transpose the vertices and then do a matrix multiplication with the rotation matrix, and then untranspose the result. And why do we need to do this transpose? Well, there's kind of a convention that when you're describing rotation matrices, you are imagining that those matrices are operating on points where the points are column vectors, not row vectors. But we do want to store the points as row vectors, so we have to do this transposition. So like rotation matrix here is 3x3, verts is n by 3, right? So when we do matrix multiplication, the inner dimensions have to match. So we have to do that transposition first. So we do, we have 3 by 3 by 3 by n. The inner 3's go away and we're left with a 3 by n, and then we have to transpose that back. So that's all that's happening here. And that's just a standard convention for rotation matrices. Yeah, and you could also write this numpy dot. You could also write this as a matrix multiplication like this. I think this code might have been originally written before that was an operator, though. So, and all these kinds of functions you could just write on the fly. But I think it's a little clear sometimes to just be explicit about things and wrap them in functions. Then you can add nice little checks like checking the shapes of things. You can handle things like I have like a rotate vec function for like rotating a single vector, and that kind of handles the extra dimension adding and removing and stuff that has to be done. And then you just don't have to think about that stuff in the future. Yeah, so this is all just handling transforming meshes and points by our kind of goofy transformation representation that we have. Yeah, scaling parts, mirroring parts. So that's something that happens that's kind of useful is you want to mirror parts, especially like I think you'll notice I only have functions for mirroring across the x-axis because that's the lateral, like I'm building spaceships that, the long axis is y, left and right is x, and up and down is z, so I'm often mirroring things across. Yep, and then I have a functionality for saving out models. So this might be something that we have to look at a little bit here today. And this basically saves a parts dictionary, or it saves a mesh to a number of different formats, and it's intended to be used in conjunction with this function, which saves a whole dictionary of parts to a few files. There's like a folder that contains egg files for Panda 3D. There's a pickle file, potentially. You can also save OBJ files or a JSON file. So there's like a number of different formats that this can all kind of save at once. And let's see what else we have here. Yeah, just converting transformations into the right format. I think, again, some of this could be replaced by just enforcing that things are correct earlier in the process. Adding a prefix or suffix to part set, setting parents to non-parent parts. I'm wondering where I actually use that. I don't recall writing this. Adding prefixes, just kind of common operations. Concatenating dictionaries, so just easy ways so I don't have to think about the right syntax for concatenating multiple dictionaries together. Although you can just do this for multiple dictionaries, so this isn't, I don't always use this. Yeah, applying a function while adding a suffix. So like if you want to create a mirrored version of a part set and add a suffix at the same time, for instance. And then some functions for applying a function across the part set, or applying a function to models using multiprocessing. So that comes in handy for certain times. Spin is just a quick way to spin a model around an axis to make other parts. This should probably go somewhere else. since it's kind of a more specific thing than just the parts set itself. Finding roots, multiple roots, single roots, validating checking and making an assertion fail if a part has more than one root. So that's all the functionality. It's about 1,100 lines. Here, you know, it's depending on some mesh utility stuff. But here's the functionality that I want to add. A common thing that I'm finding myself wanting to do is to be able to store extra models in a part set that are in the hierarchy, but I want to be able to kind of like turn them on and off. Like sometimes I want to view them, sometimes I don't. Maybe when I'm loading a part set into the game engine, maybe I want to load these things, maybe I don't. I have a pipeline for building different versions of part sets for different levels of detail. And that's fine, but within one part set, I want to be able to turn things on and off. And the main thing that I want to use this for is I need to do actual proper collision handling in my game. So the way collision handling works right now is I have kind of these hard-coded collision boxes that are attached to the game entity and aren't really loaded in from the file. And the problem is like I don't want to have to rewrite these as I change the model. Like they should just be generated along with the parts when I run the script that generates the parts, or if I tweak dimensions or whatever, these should be updated. So they should somehow be there in the parts, but I don't want to always look at them. I want to be able to turn them on and off, or better yet, I might want to, you know, view them like with some kind of transparent color while the rest of the model is opaque, right? To be able to verify that these collision solids I might be making are appropriately sized. Another thing is that you can do a lot with collision, like some of their built-in collision primitives like spheres and capsules and boxes and stuff, but really to do things correctly, I'm going to need to make custom collision geometry that I load in, and I want to start in on doing that. So this will be a step towards that as well. So there's nothing that really stops me from doing this already, right? I can just add in different shapes and have them be there in the part set. And I can even exclude them from being loaded along with the rest of the model. What I don't have is maybe a nice way to view it, and I don't have a convention for how I'm tagging them. So I want to build a viewer function, a special viewer function that recognizes that convention and shows things in a special way, and then I can and then I'll test out maybe like building some collision solids for different models. So let's try this out. So let's go into the Ashinoko here, and we'll try to build a low poly collision shape for the fuselage that will kind of like correspond to the general shape of it. and we'll attach it, and then we can figure out how to exclude it from the model in the game while visualizing it in the parts properly. Okay, so let's take a look at some of these different pieces here. So the fuselage I have constructed from these two different pieces. So let's just take a look at them. Whoops. On the right script here. So we have this piece, and then we have this hexagonal piece. So I'm wondering if we take the original fuselage shape, which basically doesn't have the bevel, and if that would kind of be a good approximation for what's going on, because we want sort of a low poly approximation of the shape. Okay, doesn't look like there's a great way to get that. Well, how about this? How about just for starters? We'll just use a cylinder. And this is just an approximation, but gotta shift this back. I think this is correct here. Oops. Let's just take a look at the two of these together. Oops. not translating this correctly. So, oh, I want to actually translate it forward by that amount. Whoops. Need to figure out here how this fuselage is lined up. So yeah. Okay, so I was right in where things are aligned. Now, how do I have to shift this? These subtractions that you have to do to line things up are sometimes a little bit tricky to do. So I think we have the total length correct. So the center is there. So the current center is at 0. Where we want the center to be is, oh, we need to just shift yeah, we need to shift it forward. Yeah, okay, so the cylinder center is at 0. We want it to be at the total length minus, let's see here. Yeah, we need to shift it forward by the difference between half of it and the current amount that sticks out the back. Which is yep, length minus 2 minus so let's see here. Let's see if this is right. So minus whew, that is wrong. Oh, there we go. That seems to line up. Seems to line up the middle with the end of it. Oh. There we go. Okay, there it is. All right, so yeah, let's rotate this to 90 degrees. There we go. Okay. Now this is obviously not accurate, but it's like sort of a start for now. So what we want to do is we want to add this into our hierarchy, but we want to be able to distinguish it from the other parts. And for different purposes. So let's just add it in right here. I'll just call it fuselage collider because that's kind of what it is. And we'll add a property. So we'll add a property to be a, we'll just call it tag. So now if we run our bench again, we should see our part set, yeah, with that big mesh in the way. So now just want to add a convention that allows us to either filter that out when we're viewing it, or view it with a special color or transparency or something. Okay. So what I'm thinking is something like view parts, but we'll call it view parts filter. And just for now, we will assume that there's only a single root in our parts list, because I just don't want to, it's busy work to deal with that extra case right now. So we'll just assert that there's just one root. And okay, so we're going to find our meshes, and then we'll look at a filter function. So the filter func here, that we'll take something and we'll say meshes equals kv for items if filter func of v. Now we could do kv here. Yeah, we'll do kv because then we could filter on the name or whatever too if we wanted to. And then we can view meshes. So we can do something like this. So this is our standard view. And then we can say parts filter. And then we can do a lambda of v where we can say v.props.get tag none does not equal collider. Oops. Okay, that's interesting. Did not expect that. Oh, that's the list of meshes. I need to be looking at the parts here. So actually we'll do our filter first. This is pretty simple, but I have a specific way in mind that I want to extend this here. There's no attribute shape. What's going on here? So we're getting to that line. Let's see here. Oh, view meshes. I don't want view meshes. I want view mesh and flatten parts. Yeah, okay. So that is working. Now what I want is something a little bit more advanced where I can filter parts, but basically assign like a transparent color to the parts that I'm filtering out, so I can see the original like the core of the thing along with these other parts. So let's implement that now. So let's filter. And just for the sake of being simple, we don't need to like have different filters and different colors. We can just have a single filter function and a color. I think that's a good interface. So we'll start kind of with the same thing here. Now here we want to do this a little bit differently. So here we want to do the and what does this guy return? Yeah, this guy does return. This is what we want. So okay, so this is going to return a list of transformed meshes. And let's see. Yeah. Okay, and this is good. I'm gonna refactor this too. So I have this function called view meshes that automatically assigns face colors to a list of meshes. I'm gonna refactor this so I have a function called like view meshes colors that doesn't automatically assign colors. And then we can use that to assign specific colors to meshes here. So yeah, see, I've got a note for myself, maybe a different interface where colors are passed in here. So we'll actually do a list of tuples of mesh and color. And we'll just make color be any for now. It's the thought that counts there rather than what exactly it is. This will be meshes, colors up to the length of meshes. this will be for mesh color in colors, and we can just replace this with color, and oh, and this logic can go, because this actually has to go in here. Because we have to repeat, so this. Sure, there's a nice built-in to do this. I don't care. I'm just dashing it out. Yeah. Index. Why is this grayed out? Local variable index is not used. It's used. Come on. Oh. There we go. Yeah. There's a much nicer way to do that, but we'll focus on this. So now we're going to concatenate yep. Okay, so yeah, we're building okay, so now what we can do here is we can build our list of colors. So colors is this, and then for this is a dictionary, right? Yeah. So for name mesh in meshes.items, we find the original part as parts of name, and then if filter func of let's see here. Yeah, filter func of name part, then yeah, so actually we'll have two colors. So we'll have keep color base. So color base else. Actually, we can do meshes with colors right here, meshes with colors, and we can both and we don't need this anymore. Now we can util.view meshes colors, meshes with colors. All right, cool. Okay, so this should do what we want. Let's run it and fix what's wrong. So the base filter view. Okay, so we're gonna have exactly the same, and let's put in the argument names here. Parts, filter func, parts. Filter func, color, So color base is, we'll do a nice gray. So we'll do a nice gray, 255, and then color filter. We'll do a green that is transparent. We'll do a bright green at like very transparent. Yep, look at that, perfect. And something that you run into when you do this transparent rendering is it's a little glitchy. You know, you can see it kind of like chopping out certain things. Did it actually chop out the... No, that's funny. Yeah, but you can see, at least you can kind of see in the wireframe that everything is still there. That might be something to play with in terms of, I need to come up with a better like internal viewer as well. That might be something to play with there. Yeah, really what I think what needs to happen here. Yeah, I wonder what's causing that, because is it like a, must be a depth buffer thing. Because we're seeing this. So this would be drawn first. Yeah, some kind of depth sorting thing. Let me actually just do a quick little bit of looking here. If there's a way in PyRender to disable, I could disable depth. Only render the depth buffer. Because yeah, if I disabled the depth buffer, that would probably fix that issue. Yeah, I'm not seeing a whole lot of control over that. Yeah. Oh, here we go. Here we go. So mask alpha mode. Opaque, the alpha value is ignored. Mask, the rendered output is either fully opaque or fully transparent. Blend. Let me see if I can set alpha mode and see if that fixes it. Oh, that's a material thing here. So, default material. Let's see, where's my material coming in? Oh, okay. Yeah, so let's just try this. So material equals high render material alpha mode equals blend. Let's see what this does. All right, well that just completely screws it up. Seems to get rid of the colors too, which is not good. Let's see here. Anything else we can tweak here? Is visible. And this is returning a mesh. Let me just see if there's anything in mesh that, oh. We can do it is transparent. So we could try, let's just try this. So oh, you know, another, yeah, the problem is that this is all one mesh too. Like that's part of the problem is, and that's almost certainly why it's not showing, because it's a self it's like a self intersection too. Can't set attribute. Shucks. Trimesh is visible, wire smooth. Yeah, so I think it's going to take a little bit more work, unfortunately, to get a decent like a decent like actual overlay here, kind of due to the way my viewer works. But that's more of a viewer problem. I think let's just do something quick here to make sure that we can filter this collision solid out in the model, and then we'll call it good for today. And I'm going to look into maybe a nicer wrapper for this, maybe where I can put multiple meshes in. Multiple meshes in, and I think that will solve that semi-transparent problem as well. If we could just build a separate transparent mesh here and pass into, I think that would fix our problem as well. So let's just save this out, and we'll see if I bring this up in the ship viewer now, we should see that big solid in the way. Oh, nope, it's not there. Oh, I know why. Because it's not actually, I parented it to root. Yeah. All right, well, we'll parent this to fuselage and see. We run the bench, what it looks like. It should look the same, I think. Yep, and now if we Yep. Okay, so there it was. Now we should just be able to exclude it using slider like this, and we call it, yeah, fuselage collider, and then it shouldn't be there anymore. Yep. Okay, cool. So now it's there. Now it would just be adding in logic to, you know, if we wanted to specify that part for being a collision object in the entity, or however I want to do that. But we've got the we've got that capability. So, actually, why don't we just do this? I think that we can very quickly refactor this this to take multiple meshes, and that I think will fix our problem. So let's do that. So this will be, we'll keep the same interface for this because I use this all over the place. I don't want to break it. Actually, let's take a look. Meshes with colors. Yeah, this, yeah, and then we'll build yeah, instead of building a single mesh here, we'll actually build multiple. So, and meshes FC. So we want this to be able to take a different material for each mesh. So okay, and this doesn't exist yet, obviously. So this is just viewing a single material, but we're going to do view meshes with mats, and this we'll call this just by making a list of this. So, and this just has to go in a loop. So for mesh mat in meshes with mats, and there's no scene hierarchy or anything. It's just going to be flat. Okay, now multiple. I think I called it view multiple. Yep. So now we just got to build the other side of it here, and then we'll be good to go. Meshes with colors. So original method, we built a single mesh. Yeah, so this is actually going to get a little easier now. Meshes FC is just going to take a tuple of, yeah, meshes and face colors. So this actually, yeah, we don't really even need this anymore because it's just a simple it's just a simple call. So we can actually just go util.view meshes FC meshes with colors. Whoops. Okay, that looks like it was sort of working, except we didn't have colors. But we'll back up and take a look. So let's get rid of all this extra viewer stuff so we know we're just looking at what we think we're looking at. Standard view, and then the filtered with colors version. And I'm going to get rid of this. No, we want that. Okay. Oh, that's unfortunate. Oh, that's why. Yeah. No, maybe not. Yeah, okay, so that's weird. It's like the face colors aren't applying. Let me see here. Let's just give everything the filter color. See what that does. It's probably just a very simple issue here. Let's change this to something more obvious. Yep, okay, so it's like it's not taking the color at all now. Weird. I might have to debug this offline a little bit to figure out what's going on, because could be something oh, I know what's going on here. I know what's going on. I need to actually, jeez. Okay. I know what's going on. So I need to, I still do, there was one piece of functionality that was missing. So I do need to expand these face colors out. So let's see. So I need to do face colors of this mesh. Because that's expecting a, it's expecting a it's expecting a full list of face colors, not just a single color. No, still not working. That's weird. Okay, well, I'm gonna take this offline and try to figure out what's going on here with this viewer, but I think we got a good start on this, and you know, most of the problems that we had here are just kind of like viewer issues, not really fundamental ideas with this approach. I think like having a tag that we can use to filter these shapes and build them while we're building the ships is a good idea. So thanks for everyone who watched. I'll be streaming again soon with more updates. I've got some interesting stuff in the works here with this project. I'm getting back into some high detail modeling. I'll probably do that on stream too. So stay tuned for that. But thanks again. Have a good rest of your day, and I'll see you next time.